So as Chris mentioned, we've been in business about 13 years. We started the company in 2001. We had extensive experience in embedded database systems and in embedded systems. And from our earlier experience with other embedded database companies, trying to apply those embedded databases to problems in embedded systems, we knew that there was a need for a type of database that wasn't being adequately served by the existing database vendors. Specifically, that was for an in-memory embedded database system with a small footprint. There were a few in-memory database systems, most notably X10 and Polyhedra, but those were large footprint SQL and or client-server type products that weren't really suitable for embedded systems. And there were also a lot of so-called embedded databases, but most of those were written in the 1980s, and they were intended to be embedded into business applications, not in embedded systems, because no one was using embedded databases in 8 and 16-bit embedded systems back in the 80s. So we created eXtremeDB, and we started McObject to launch the first in-memory embedded database system that was written explicitly for embedded systems. And it's worth mentioning that initially targeting embedded systems doesn't preclude you from tackling bigger systems later on, as we have, but you can't go the other way. You can't write a database system that's targeted for enterprise or large server systems and then expect to be able to apply it to embedded systems with all the resource constraints that are embodied in those embedded systems. You have to design and write the database system from the very first day with the awareness that it's going to be executing in resource-constrained systems with a rudimentary operating system and so on. Well, due to our success in creating and defining a new segment of the database market, that being the in-memory embedded database, there have been others that have followed us, but we continue to define the market by leading with platform support, new features, and market share. No other products really compare to eXtremeDB's breadth and depth for this space. One example of that leadership was back in March of 2003 when we introduced the first version of eXtremeDB High Availability. So one example of use of eXtremeDB-HA is in network and telecommunications. In fact, most of our customers in the network and telecom space employ eXtremeDB High Availability. For example, Hutchison Telecom has implemented real-time call management with eXtremeDB-HA for their Hong Kong and Macau mobile phone roaming system. So Hutchison makes money when its subscribers have calls connected and they're consuming minutes and other services. Yet the system is unavailable, even for a very short period of time, multiplied by the number of users on the system. The cost of a service interruption is really very large. But with eXtremeDB-HA, Hutchison hasn't had a service interruption in the 6 or 7 years that the system's been in operation. Whenever there's been a failure, the failover has in fact worked to a standby system. Boeing's another good case of HA, in this case in aerospace. They licensed eXtremeDB-HA for a project with the Apache AH-64D attack helicopter, which we saw on the previous slide. So this system stores navigation data that's transmitted between ground and air systems, and as you might expect, nearly every flight-related system is redundant, and this is no exception. And then financial applications represent another use case that's a bit different than the others. So in some cases, the motivation might be the same. In other words, provide operational continuity for a regional exchange, for example. But often it's to distribute the database through HA replication to the trader's workstations so that queries can execute against the local copy of an in-memory database to get the maximum performance relative to executing a query against a remote copy of the database sitting on a server somewhere. So there's different business justifications for having high availability. It might be because you need the continuity of a high availability system such as Hutchison, or because it's a safety critical system like in the case of Boeing, or it's for performance optimization reasons as in the examples of our customers from the financial markets. So a key requirement of many embedded and especially real-time systems is predictable performance. The time that it takes to insert, update, or delete a row or a record or an object in the database shouldn't vary wildly from one execution to the next. Likewise, the time to process the exact same query or a read request should be consistent over time. To the maximum extent possible, these metrics should be constant irrespective of network traffic, server load, and other variables. So we'll talk about how predictability can be assured through the features of eXtremeDB-HA. Predictability on its own is no good if it just means predictably bad. So we also want good, in fact, even excellent performance for all operations. So we'll look at the design choices for high availability and how performance is impacted by those choices. And when we're talking in the context of high availability, the need for reliability should be self-evident. After all, the goal of high availability is for the outside world to experience the system as a reliable one. In other words, it's there when we want it or when we need it. So high availability involves redundant systems with a backup system to continue to make the system available if the primary system fails. But the embedded database or the high availability subsystem should not be the cause of the failure that triggered the failover to that standby system. So we're going to look at some factors of eXtremeDB that contribute to its reliability, and as a corollary, how the absence of similar features may cast some doubt on the reliability of alternatives that you might consider. So in the next few slides, we're going to cover the basic concepts of high availability and explain some of the terminology that's frequently used. Like most technologies, it has its own vocabulary, so you need to be familiar with it to sort through the information that's going to be available from just about any resource. So first, database systems have a concept called the ACID properties of transactions. Supporting transactions with the ACID properties is a litmus test of sorts for any database system. If a purported database system doesn't support the ACID properties, then an argument can be made that it's not really a database system at all. At best, it's a record manager. Now, it is the case that in the last few years, a new breed of databases have emerged called NoSQL databases that, by and large, support a different set of properties called the base properties. Similar to ACID, but different. An examination of those differences really goes beyond the scope of our conversation today. So for today, I'm just going to focus on the ACID properties. So ACID is an acronym for atomicity, consistency, isolation, and durability. So atomicity is the all-or-nothing property. So applying a group of changes to a database should all happen or none of it happens. So it's an atomic operation. Consistency has a couple of meanings. First of all, applying consistency or applying a transaction to the database moves that database from one consistent state to a new consistent state. And then secondly, this property means that every client of the database has a consistent view of the database. In other words, the database looks the same to everybody. It's closely related to the isolation property, which says that any changes that are being made within a transaction can't be seen by any other client. So those changes are isolated to that one transaction, which lends to that consistent view. And then finally, durability says that once the database management system acknowledges a transaction commit, that data is durable. So you always have to take durability in the context of what the media is for your database. So for an in-memory database, it's durable as long as the in-memory database itself is durable. But actually, you can apply that principle to an on-disk database as well. That transaction is durable as long as the on-disk database itself is durable. But if you have a head crash, suddenly you don't have an on-disk database anymore. So if durability is that important to you, you better have some backup, no matter what your media is for the database. Okay, database replication is the process of duplicating or producing a copy of the database. High availability databases achieve high availability through database replication. The implementation of replication can be based upon replicating transactions or replicating individual database objects, which could be columns, rows, or database pages, or it could be done by replicating database modification language statements, or DML statements, if you will. So if you're using an SQL database, instead of replicating the data, we can replicate the SQL insert, update, and delete statements. Arguably, transaction replication is the best because it has the ability to preserve the logical consistency of the database, just like the ACID properties do. However, replication can be done at several levels. For example, there could be the equivalent of a trigger that pushes inserts, updates, and deletes of rows of a table out to replicas. Or the replication engine can push entire database pages, not columns or rows, but entire database pages. In addition, the replication can be in real time, or it can be transaction log based, or as I mentioned, it could be based on SQL statements. And in the latter two cases, it could be a separate process that's picking up data as it's appended to a transaction log file or to a file containing database statements, and then that's transmitted to the replicas. It could even be pulled from the replicas. So instead of being pushed by the master, it's being pulled by the replicas. So lots of ways of doing this, and different vendors implement it different ways. One of the goals of high availability is, or should be, to replicate not just the database contents, but also the state of the system. So there's often several processes that constitute a single system, and not all of those processes may be associated with the database. But those, what I'll call unassociated systems, may still have dependencies on the database. For example, you could have a protocol stack in a chassis management system that needs to know about some quality of service parameter that's changed. So the protocol stack itself is not a database client, but if something in the database changes the quality of service parameters, that protocol stack still needs to know about it. So normally this occurs through database event notifications or triggers. And then ideally, when the database changes are replicated to a standby copy, that replication will trigger the same events and in the same order so that the standby can mirror the state of the master system accurately and completely. If the database high availability subsystem doesn't do that for you, then you're going to have more work to do at the application level to effectively replicate the state of the system. In addition to the different mechanics for replication that I talked about, there's different categorizations of high availability systems. These are eager, also called synchronous or two-safe, and lazy, which is also called asynchronous and one-safe. And for eXtremeDB, we have a time-cognizant two-phase commit protocol. So I'm going to walk through each of these. So two-safe replication is so named because there's considered to be two completely synchronized copies of the database at all points in time. This is accomplished by affecting the replication in a synchronous manner. In other words, the master copy is blocked until the transaction is replicated to the standby copy, or copies if there's more than one, and only then is control returned back to the master application, which then can continue processing. This is also called eager replication, as I mentioned, and this approach eliminates conflicts because the master and the standby copies are updated in lockstep. So it's a potentially less complex solution. Therefore, there's less code involved, which means a smaller footprint, and less complexity generally means less prone to defects. It also has the advantage of ensuring that every copy of the database is identical at all times. So a query issued against any copy of the database, a master or one of the replicas, is going to yield the same result set as if it was issued against any other copy of the database. So assuming that the database system allows replicas to be read by local processes, and eXtremeDB does, this means that a query executed anywhere is going to have the same result set as if it was issued against the master database. So our queries can be distributed or spread throughout the system for some load balancing. Now, on the negative side of the ledger, the synchronous nature of the two-safe model means that the throughput is not exceptionally high. Remember, the master is going to be blocked while the replicas are applying the transaction to their copies of the database. And we do get some parallelism with eXtremeDB's implementation here. So with eXtremeDB, the master is going to be updating its indexes while it's waiting for that reply from the replicas. So the master isn't completely idle. It's still getting some things done while the replicas are doing their part of the work. But it's still the case that the master is going to be blocked until that reply comes back from the replica. So as I mentioned on the previous slide, eXtremeDB High Availability implements two-safe replication through what we call a time-cognizant two-phase commit protocol. So that's a mouthful. Let me break it down. First of all, it's a two-phase commit protocol. So the commit is started on the master, and then once the master knows that it's going to be able to successfully commit that transaction, it sends that transaction data through the communication channel to the replica and then waits on the replicas to do their part of the commit. The replicas apply that transaction to their local database copies and then send the return code as a reply back to the master. And then the master compares its own return code from applying the transaction to the replica's return code and does the final phase of the commit. Now, because the transactions are synchronous and the databases are identical at all points in time, if a transaction is going to succeed on the master database, then it also has to succeed on the replica databases. They're identical. If it succeeds on the master, it's got to succeed on the replica. So if the replica gives back any other return code other than success, that indicates that there's just something fundamentally wrong with the replica. And so in that case, the master is just going to decommission that replica and go ahead and finalize the commit on its own copy of the database. And that replica will then have to reconnect to the master and get resynchronized. And then the second part of this, the time cognizance, that's the matter in which eXtremeDB gains back predictability in the context of unpredictable network latency. So every communication between the master and the replica has a timeout associated with it. And there's 4 types of communication. First of all, there's that initial synchronization step. So when a replica connects to a master for the first time, we need to send a copy of the master's database through the communication channel to the replica to get them into this initially synchronized state. Then we can start replicating transactions. So the time that it takes to send the database through the communication channel to the replica has a time limit associated with it. And if we can't get it done within that time limit, then we'll give up and we'll return control back to the master application. The second communication is at the transaction commit. So the master is going to send the transaction data through the communication channel to the replica, and there's a prescribed amount of time to get that done. And again, if it can't get done within that period of time, either because the network is congested or the replica failed or something, then we're going to give up and return control back to your application. The third communication is after the replica has that transaction data, it needs to apply it to its copy of the database and send the return code. So the time that it takes to get that return code back from the replica has a time limit associated with it, and the master won't wait longer than that. If it doesn't get that return code, it'll decommission that replica and return control back to your application. And then the last communication is really a heartbeat. The replica is going to expect to receive a heartbeat signal or a transaction from the master every n microseconds or milliseconds or seconds, whatever your threshold is. And if it doesn't receive either a transaction or a heartbeat within that period of time, it's going to assume that the master isn't there anymore, and we'll begin the failover process. And we'll talk more about the failover process later in the presentation. Okay, so that was two-safe replication. Conversely, one-safe, as its name implies, has lower consistency. You've only got one safe copy of the database, but it will exhibit better and perhaps much better performance due to its asynchronous nature. So in this case, the master isn't blocked while the replicas apply the transaction to their local copies. Instead, the master is going to finish the commit on its own system, and once the commit has succeeded, then it sends the transaction data through the communication channel to the replicas and immediately returns control back to the application. It doesn't wait for the replicas to do their part of the commit. So in general, because the master doesn't wait, the one-safe model can introduce the possibility of conflicts that then have to be resolved through some reconciliation process, and that would naturally complicate the implementation. But in the specific case of eXtremeDB, there is no possibility of conflicts even with the one-safe model. What you do give up with a one-safe model is that guarantee that the result set from a query is going to be identical no matter which copy of the database you send it to. Because now there's going to be some lag between when a transaction was committed on the master and when it gets committed on the replica. They're not being done in lockstep anymore. So you lose that guarantee. And what you get back is, as I said, better, and in many cases, much better performance. All right, continuing on with our concepts and definitions here. I briefly mentioned initial synchronization already. That's the process that happens when when a replica attaches to a master database. So before we can start replicating transactions, the master and the replica have to be in an initially consistent state. So the master sends a copy of its database to the replica through the communication channel. As a brief side note here, we don't necessarily send the entire database. So if you've got a 100 megabyte in-memory database, just to pick a number, just to pick another number, say 60% of that database consists of indexes, not data. So we're only going to send the data pages through, and we'll rebuild the indexes on the replica side as the data pages are being received. All right, so depending on the speed of the communication channel and the size of the database and the speed of the CPUs and the application's response requirements, that initial synchronization step can still take too long, even though we're not sending index pages. So in that case, we can use a feature that we call hot synchronization. So the normal case with static synchronization is that the master database is read-only during the initial synchronization, and any write transactions get queued up until the initial synchronization is complete. And this allows the initial synchronization to progress as fast as it possibly can. But again, that can still be not fast enough. So with hot synchronization, we do allow write transactions to happen concurrently with the initial synchronization, and then an algorithm is employed that will cycle through the database pages to resend pages that were modified after they were transmitted, but before the initial synchronization was completed. So as a consequence, the initial synchronization is going to take longer to complete. First of all, the initial synchronization is running in parallel with other transactions, so it's just busier. And then secondly, we might have to retransmit pages because they were modified after we first transmitted them, but before the initial synchronization was entirely complete. But our goal for hot synchronization was to not degrade the performance of the master by any more than 30%. All right, sometimes there are spurious network errors that cause a temporary loss of the communication channel between the master and the replica. We call this network flapping. In this case, a complete resynchronization of the replica would be overkill. So to address this, eXtremeDB implements what we call stateful replication, which means that a master and a replica can be made aware of each other's state, which permits the master to retransmit only the transactions that the replica missed while it was briefly disconnected. So to accommodate this, the master maintains a programmer-defined size buffer of the most recent N transactions. And then there's a handshake between the master and the replica that includes the exchange of a transaction sequence counter. And that way the master can tell how many transactions the replica missed. And if it still has those transactions in its buffer, it can just retransmit those transactions in lieu of doing the whole initial synchronization step. So that value of N is going to be a function of how big a buffer you allocated, how fast the master is applying transactions to the database, and how large those transactions are. All right, sometimes a replica doesn't exist for the purpose of taking over in the case of a master failure. Rather, the replica exists to provide fast local access to the database versus having to communicate over the network with a remote database. So the financial system trading example is an example of that. But it's also often the case in this scenario that the replica doesn't need the entire database. So, for example, going back to the network chassis management system, they'll often have a master and standby controller board, and then at least one line card for each supported protocol. And in that setting, the line cards for the protocols will only need a subset of the database that's related to that specific protocol. On the other hand, the standby controller card is going to need the entire database for failover purposes. So to support the line cards requirements, partial replication can be implemented. And that can be supported in a variety of database vendor-specific ways. In eXtremeDB, we do it through through data definition language keywords to indicate that tables are strictly local, or that they can be replicated on demand, or that they're just automatically replicated. And while the master standby model satisfies high availability requirements, it doesn't scale very well because all the inserts, updates, and deletes have to be applied to the master, which then propagates them out to the replicas. So when processes that are not local to the node where the master database resides need to update the database, they have to do that through a network connection, which necessarily involves a round trip. In other words, send the data and then receive a reply. So, of course, this is a performance issue for the remote process because now you're introducing network latency. And in addition, it makes the master a potential source of congestion if there's a lot of updates from a lot of remote processes. Of course, if there's only a few updates and only a few remote processes, which is often the case in embedded systems, then a single master solution is still going to be the preferred solution due to its simplicity. But when that's not the case, then a cluster solution that permits any or all of the databases or database instances to be updated answers that congestion issue and also the network latency round trip issue for a client wanting to update a database, and thereby also addresses the scaling question. So in that configuration, any database can be updated, or any database instance can be updated, and will propagate its changes to all the other copies. Now, this vastly increases the potential for conflicts, and resolving conflicts can be a complex problem to solve, but in practice, it's often the case that the division of labor amongst the processes is such that they rarely, and sometimes never, induce any conflicts. In other words, process A is responsible for its part of the database, and process B is responsible for its own different part of the database. So there's inherently no conflicts in that situation. So let's look at the different replication models here. So this is your typical single master with one or more replica model, and this is going to satisfy the vast majority of the use cases. But you can get a little more complex, and eXtremeDB supports this model of cascading replication. So you still have a single master, but a replica to that master can also act as a master to other replicas that are further downstream. And again, this is probably overly complex for most systems. And then the cluster model, in which every node in the cluster needs to have a communication channel open to every other node in the cluster. So you can imagine that as we start adding nodes to the cluster, the network of interconnections can get rather messy. So eXtremeDB has its roots as an in-memory database. It's evolved since 2001 to now also offer on-disk storage through our eXtremeDB Fusion product. And eXtremeDB High Availability works with either storage model for in-memory databases as well as on-disk databases or hybrids of in-memory and on-disk. But in reality, the types of systems for which eXtremeDB is selected are often able to store the entire database in memory, and in fact, that's precisely the reason that eXtremeDB is selected, because it is an in-memory database. And the customer needs an in-memory database for the performance that they can only get from an in-memory database system. But there's still a lingering concern that in-memory databases are somehow more volatile or more risky than on-disk databases. But as this quote from IBM that goes back to 2003 illustrates, those of us in the industry have long known that the technology exists to make in-memory databases just as reliable and durable as on-disk database systems. And I think the proliferation of in-memory databases in the last 4 or 5 years validates that. So today we're looking at 2 ways of achieving reliability for in-memory database systems. High availability primarily, and then we'll also take a look at transaction logging. So the purpose of high availability is just as the name implies. It's to preserve the availability of the system even in the face of failure of one of its parts. The purpose of durability, which is implemented through transaction logging for an in-memory database, is to ensure the survival of the database in the event of a catastrophic, in other words, a system-wide failure. For example, if a system is housed within a single physical plant and that entire physical plant loses power, which is going to cause the master and the replicas to all terminate. So in that case, you would need durability to be able to survive that. So a couple of slides ago, we looked at some possible replication models, the single master, multiple replicas, and cluster, and so on. On this slide, we're seeing 2 common examples of the physical arrangement of HA systems. Specifically, you can have 2 or more computers that are connected through a local or a wide area network. And in the second example on the right, you can have a chassis with multiple boards that are connected by a backplane. The physical arrangement of the systems is independent of the replication model. Again, whether it's 1 safe or 2 safe, and so on. So at this point in the presentation, the remaining information is going to be specific to ExtremeDB high availability and ExtremeDB transaction logging. So everything up to this point has been kind of vendor neutral. It's been talking about concepts and definitions and models and whatnot, but at this point it's going to get specific to ExtremeDB. So ExtremeDB-HA is implemented independent of the core of the ExtremeDB runtime. In other words, the core of ExtremeDB itself really doesn't know anything about HA, or even whether it's present or absent. And then ExtremeDB-HA itself is implemented in a modular fashion. So working from the top down on the diagram on the right, we start with several possible communication protocols to the network. So we've implemented communication channels over TCP/IP, UDP/IP, with guaranteed delivery, name pipes, QNX messaging, and multicast. So there's two layers to HA. There's what we call the protocol layer, which is our implementation of replication over multicast and TCP/IP, etc. And then there's the interface layer, which is how your application interfaces with HA, and the HA layer abstracts all the protocol-specific details away from your application, so it doesn't have to worry about whether the communication is over TCP/IP or QNX messaging. And because of this modular implementation and the fact that we provide several ready-made communication channels, it's going to be relatively straightforward for you to implement your own custom communication channel. So if you wanted to do a communication channel over a VME bus, for example, it'd be fairly straightforward to do that. So on this slide, we're seeing another view of the internal organization of an ExtremeDB-HA-enabled application with colored-coded boxes to illustrate what's implemented by you, the application programmer, what's implemented within the HA framework, and what's implemented within the ExtremeDB core. So we can see at a high level the steps that the master and the replica carry out and the communication that transpires between the two. So first the master application creates the master database and then begins to listen for replicas that want to attach to it. The replica's request to attach is represented by the box labeled connect, and then the communication channel is established in the box labeled accept. After the communication channel has been established, the initial synchronization that I described earlier starts, and that's represented by the gray boxes labeled send and receive, and all that exists within the HA framework. It just happens. Your application doesn't have to do anything other than request the replica to connect to the master, and then things just start happening. And then thereafter, the protocol layer of the HA framework has responsibility for replicating transactions from the master and applying them to the replica. Your application, again, doesn't have to do anything unusual. It just begins and commits transactions in the normal way, and the protocol layer of HA takes care of all the replication stuff behind the scenes, transparent to the application. So now we're going to look at the specific steps that are needed to incorporate high availability into an ExtremeDB application, starting with the master. So every ExtremeDB application has to open the database and establish a connection to the database. And one of the rules of programming with ExtremeDB is that every thread and every process has to have its own connection handle. So you're going to, in the left-hand side gray box, you see the McODB open. That's how we open the database. And then once we've opened the database, we call McODB connect and get a connection handle to that database. So the first step to incorporate HA is the call to McO-HA set master params. And this function is used to establish all the HA parameters. For example, whether the replication is going to be one safe or two safe, and if it's two safe, then also those timeout parameters for each of the communication steps that I talked about before, the size of the transaction buffer if you're using stateful replication, and all the other user-definable parameters are set up in that one structure that's passed into McO-HA set master params. And then the next step on the master side is to spawn a thread in which the master is going to listen for replicas that are requesting to connect. And the thread function is shown on the right-hand side of the screen. And it's really simple. It just executes an infinite loop listening on a port for a connection request. When a connection request is received, then McObject attach replica performs the initial synchronization, and then loops around and waits for another connection request. And of course, the protocol layer of eXtremeDB-HA has now squirreled away a bunch of information so that when a transaction is committed subsequent to the initial synchronization step, the protocol layer knows how to pick up that transaction and transmit it to the replicas. But back in the main application on the left side, note that the body of the application is completely unaware of whether the application is HA enabled or not. It just begins and commits transactions in the normal way. So all the details are replicating the transaction that were, whether it's synchronous or asynchronous and so on, are completely transparent to the application because they were squirreled away in the protocol layer of the HA framework. So HA enabling a replica copy of the application is similarly simple. So the replica calls McODB open and McOHA attach master. McOHA attach master is a blocking function call. It connects to the master and it receives the database through that initial synchronization step, and then inside McOHA attach master, it sits inside an infinite loop, receiving transactions from the master and applying them to its own copy. So when this function returns, it's for one of two reasons. Either the master told it to as part of an orderly shutdown sequence, or it's because the communication channel with the master was broken, which could indicate a network failure, or it could indicate that the master itself crashed. Maybe there was a kernel panic, or the process that was running the master application just had a segmentation fault and crashed. The stop reason is going to tell you, whether it was part of an orderly shutdown sequence or because the communication channel broke. So if that return code indicates that the communication channel with the master was broken unexpectedly, then that should trigger your failover logic. So an eXtremeDB embodies what we call application-directed failover. The actual steps that the replica takes next are application-dependent. The database runtime doesn't have sufficient context or knowledge to be able to direct those actions. You really have to do that at the application level. But some steps that a replica might take are to simply try to reconnect with the master if there's a reason to believe that it was just a spurious network error. Again, if the network is just flapping, then you might just try to reconnect immediately and then continue. If there's only one replica, then you can immediately have that replica switch roles to master and then continue processing. But if you got more than one surviving replica, then there's got to be some application-specific logic for electing a new master. And eXtremeDB can provide some help in this. You can poll each of the surviving replicas to get the transaction sequence counter that each replica has, which would imply that the replica that has the highest counter, or in other words, the most recent transaction, would become the new master. Or you might just take a simpler approach. You might just establish a hierarchy for failover. In other words, replica number one, if it survived, tries to become the new master. And if it's unable to or it's not there anymore, then replica number two tries to become the new master, and so on down the line. But regardless of the mechanism of determining the new master, once there is a new master, the other surviving replicas would then attach to the new master. And then lastly on this slide, there's a special mode for McOHA attach master that can be used when the original master is restarted. So when it restarts, it comes up as a replica, but it can pass this special flag that says connect to the current master, get synchronized, and then become the master again. So the replica that became master will revert to being a replica again, and the master that crashed will resume being a master. So earlier in the presentation, I said that there's an expectation of reliability that's implicit when we're talking about high availability, and that the embedded database or its HA subsystem shouldn't itself be the cause of failure that initiates a failover. In other words, you don't want the DBMS to crash, which then cause a failover to the backup copy. But reliability is a multidimensional topic. We can refer to reliable or predictable performance, and we can also talk about reliability in the context of a measure of immunity from failures. So with respect to reliable performance, EXtremeDB has different programming interfaces, or APIs. We have an SQL API, and we have a native API. The SQL API that we've implemented includes a rule-based optimizers. So SQL optimizers come generally in two forms, cost-based and rule-based. So cost-based optimizer is inherently more complex, and it's more of a black box. You don't really know what's going on inside that optimizer, and frankly, it can be a very delicate bit of software. Cost-based optimizers, their job is to attempt to calculate the cost of each possible way of executing one step in the execution plan, and then assemble a sequence of steps that's less costly than any other combination of steps. Now, when they work well, but there's some potential problems to watch out for. First, the number of possible execution plan steps can be enormous, and the number of possible combinations of this enormous number of steps can be truly mind-boggling. And the consequence is that your program can spend an unacceptably long time in the optimizer considering all the options. So database vendors typically offer a couple of ways out by allowing you to tell the optimizer to take the best plan so far after considering the first 100,000 plans or after 500 milliseconds, for example. But then you're not guaranteed of getting the best execution plan, just the best one so far. Another approach that database vendors take is to allow you to decorate your SQL syntax with special characters that tell the database runtime to use a particular index. But once you do that, then you're locked into that particular database vendor because now you've deviated from the standard SQL language. It's also the case that cost-based optimizers can generate a different execution plan for a query that didn't change because the cost analysis is a function of the distribution of the data in the database, for example, the index histograms. So what was acceptable performance for a query in the QA lab based on the anticipated distribution of the data and discrete values in the database turns out to be unacceptable in the field with live data that's really quite different than the data that was used in the QA lab. And it can also be different from one customer to another customer because they have different types of data in the database. And then lastly, seemingly innocent changes to the SQL optimizer logic by the database vendor itself can have a disastrous effect on the performance of queries that ran fine before the so-called improved optimizer was deployed. Now, rule-based optimizers, which EXtremeDB uses, are much simpler, and they solve all these potential problems that I just described above. A rule-based optimizer applies a fixed set of rules to formulate the execution plan, and the time required to formulate the execution plan is constant. The optimizer is just going to consider rule 1 through rule n, and boom, it's done. So the rule-based optimizer isn't going to spin for an indeterminate amount of time considering umpteen gazillion different execution plans. And its execution plan is never going to change because the distribution of the data in the database changed, because that isn't a consideration. So you don't have to give the optimizer hints. You only have to understand the rules and then formulate the SQL statement in a way that the optimizer will produce the right execution plan. And that lends itself greatly to reliability. Now, native APIs, they bypass SQL altogether. So native APIs are also called navigational APIs by some database vendors. But the term navigational has nothing to do with GPS or navigation systems. It derives from the way the application programmer interacts with the database in the application code. In other words, the application navigates through the database one record at a time. That's in contrast to SQL, which is a set-oriented language. In other words, an SQL statement operates on a set of rows in the database, or in the case of a query, it returns a result set to the application. With a native programming interface, a typical sequence of steps would be to use a function to find some row in the database, for example, perform an index lookup by some value, and then act on that row, and then go get the next record and repeat. So native APIs always outperform SQL. Even the best SQL implementation can't avoid the overhead of parsing, going through optimizer, and executing the plan. In contrast, a native API just goes directly to the database tables. So consequently, a native API is many times faster. Exactly how much faster depends on the specific operations and different database vendors, but you can probably expect 4 or 5 times faster. And it's also the case that a native API is, by its nature, more deterministic, more predictable, and hence more reliable than SQL. And this goes back to SQL being a black box. The programmer controls the exact sequence of steps that's used to read or update the database with a native API and has no control over it whatsoever with SQL. Now, with respect to the other meaning of reliability, in other words, a measure of immunity to failures, EXtremeDB delivers on this by providing a native API that doesn't use void pointers. So the native API of other database systems is a predefined set of generic database functions for reading, inserting, updating, and deleting information from and to the database. And the only way for a generic function to be able to, for example, insert a record of any type into the database is to pass that function a void pointer. The advantage of that approach is that once you learn that set of database functions for a given database product, that's a skill that you can carry with you throughout your career and apply over and over again. The big disadvantage is that void pointers can't be validated by the C compiler or by the database runtime. So a simple mistake by the programmer of either passing a pointer to a type of data that the database runtime wasn't set up to expect, or passing a null pointer or a pointer that you didn't initialize enough memory for, all the problems that are associated with pointers are either going to cause database corruption or they're going to crash the application, and very likely they're going to do both. So in my 30 years in the database industry, I can tell you that the vast majority of database corruption that I've ever had to encounter and fix has been caused by void pointers. So we learned that lesson, and when we created EXtremeDB, we took a different approach to the programming interface. The native programming interface for C and C++ is generated as a byproduct of compiling the database schema. So, for example, if the database has a class called port, which has a unique identifier called port ID, the schema compiler is going to generate a programming interface that will read like port new, port delete, port ID get, port ID put, port ID find, and so on. And these functions are going to expect a handle to a port object. And if you accidentally pass a handle to any other kind of object, the C compiler just isn't going to compile that code. So that whole class of errors that's caused by void pointers is completely eliminated. And it's eliminated very early in the development cycle. And we know that the earlier we find defects, the cheaper and the quicker they are to fix. And so in the worst case, we don't find them, our customers find them, they're very expensive to fix. So we don't use pointers, we use handles to objects, and they're typed. And so that whole problem of type safety or lack of type safety of void pointers goes away. And then we build on that advantage by delivering 2 libraries for EXtremeDB, a debug library and a release library. And in the debug library, we incorporate a lot of traps and checks to make sure that you're using the database in the way that we expect you to use the database. For example, it ensures that a transaction handle is valid, that there's no attempt to use an object handle outside the scope of the transaction, and so on. So, and it also includes a lot of checks to make sure that you don't have any loose pointers in your application that are causing overwrites of critical data structures within EXtremeDB. So when your application compiles successfully and executes all your unit tests and QA and so on, then you can relink with the release library, which of course is a lot smaller and faster, and go ahead and release your application with a high degree of confidence that you've eradicated all the database-related defects in the application, and of course that contributes to reliability. Other database vendors don't have this separate debug and release versions of their database systems, and our philosophy on this goes back to our legacy in embedded systems. Embedded systems simply have higher quality expectations than PC and back-office systems do. We just wouldn't tolerate it if our cell phones crashed or our car navigation systems crashed or we had to reboot our network equipment on a regular basis to keep it running, or, worse yet, the avionics and the aircraft we're flying crashed mid-flight. So we just have higher quality expectations for embedded systems, and that's embodied in EXtremeDB. All right, now we're going to change gears a little bit and talk about durability. So you recall that I said that high availability and durability are the antidotes to in-memory database systems' perceived vulnerability. So one way to impart durability to an in-memory database is through the introduction of transaction logging. There are other ways, such as the use of non-volatile or battery-backed RAM or NVDIMMs, but today we're going to concentrate on transaction logging. So transaction logging journals the changes as they're made to the database. So if there's a crash, then EXtremeDB can recover the database from the last saved image of the database and replaying the subsequent entries in the log file. Now, it's important to note that transaction logging doesn't change the all-in-memory nature of the database. Your query performance is going to be absolutely unaffected by transaction logging, and your updates, inserts, updates, and deletes, while they will incur some additional overhead due to the file I/O that's inherent in transaction logging, still retains a significant performance advantage over conventional on-disk database systems. And the reason for that is that appending an in-memory database transaction to a log file only ever requires a single write to the file system, regardless of the size of that database transaction. It doesn't matter whether the transaction modified 1 record, 100 records, or 1,000 records, or any other number. It's still just one write to the file system to record that transaction in the log file. It's also the case that it's always a sequential write. We're always appending to the log file, and sequential writes are dramatically faster than random writes on spinning media. Not so for solid-state disks, but for spinning media, there's certainly a big performance advantage to sequential writes. Now, in contrast, an on-disk database also has to do the transaction logging, but eventually it's going to have to update the database page for each record, and it has to conduct several reads to locate the B-tree insertion point for each affected index, and then there's at least one write to update the index node, and then if that index node has to be split, or in the case of a deletion merged, then there's at least 2 more writes involved. So all in all, a simple transaction that only touches a couple of records can involve 4 to 8 or even more write operations if splits and merges are involved. So the moral of this is that even with transaction logging, an in-memory database is going to vastly outperform an on-disk database. And it doesn't matter what the media is, whether it's a solid-state disk or a spinning disk or memory tier flash device. In every case, an EXtremeDB or an in-memory database with transaction logging is going to outperform a persistent database. So on this slide, we see the code that's needed to incorporate transaction logging into an EXtremeDB-based application. Like with HA, we tried to make incorporating transaction logging as transparent to the application as possible. So in this case, we're going to open the database as usual with McODB open and McODB connect. And then we've got a few function calls that we need to make to set up the transaction logging subsystem. And then we've got the body of the application, which, like with HA, in the body of the application, you're just going to begin and commit transactions in the normal way. And the fact that transaction logging is happening or not happening is completely transparent to the body of your application. And then when you're shutting down your application, you got a couple of additional steps. You want to save the last copy of the database, and then call McOTransLogStop, which is going to remove the transaction log files, which is important for this function up above called try to recover, which we'll look at next year. So try to recover is going to load the last saved image of the database, and then it's going to look to see if there's any transaction logs laying around. Now, in the normal case, after a normal shutdown and then a restart, there are no transaction logs laying around because your call to McOTransLogStop deleted those transaction log files. So normally, this McOTranslog query info is not going to find anything to do, and just return control back to the application to continue normal processing. But if your application crashed, then you never had the opportunity to call McOTransLogStop, and there will be a transaction log file sitting on the file system, which McOTranslog query info will detect, and then we'll call McOTranslogApply and apply those transactions to the database image that we loaded from McODB load. So that's how we impart durability to an in-memory database. So, like HA, I'm sorry, I got off track here. So I'm just going to wrap up here, and then we have just a couple of minutes left for questions and answers. So it is the case that an in-memory database is often selected because of performance requirements that only an in-memory database can address, though high availability can be equally applied to on-disk databases, not only with EXtremeDB, but with other vendors' solutions as well. And then high availability itself can be mandated either by market requirements or governmental regulations. For example, here in the United States, the FCC says that telecom equipment has to be available 99.999% of the time, what we call 5 nines availability, which gives you like 5 minutes a year for system maintenance, which isn't very much. Or it can be, HA can be employed to provide some scalability, that query load distribution that I talked about earlier. And we talked about the different architectural and configuration options that you have to choose from, the 1 safe and the 2 safe, and then how the replication itself is going to be done. And all of these choices are going to affect the complexity, the performance, and the predictability or determinism of the resulting application.